Hi everyone. So this video is for factoring more challenging polynomials. These problems would only show up in an honors advanced algebra trig course. So if you just need help with basic factoring, you should watch the just regular factoring polynomials video that I put before this. So the first kind of problem though is if you look at the terms and you see x to the sixth minus y to the sixth, you would have to make a decision. You could factor those either by perfect squares or by doing perfect cubes, because you can take the square root of both of those, but you can also take the cube root of both of those. The best path to take is to factor by taking the square roots first. Because it'll allow you to factor it much farther than if you start out by factoring it into cubes first. So we are going to, let's just write the work to the side here. If we double check, the square root of x to the sixth is x to the third. Same thing, square root of y to the sixth is y to the third. So we're going to factor this into two parentheses by taking the square roots. And so we will get x to the third minus y to the third, and then x to the third plus y to the third. Okay, now if you look at your factors, both of them are perfect cubes. So we will have to factor both of these again. Now the perfect cubes pattern, I'm just doing this one first. It's going to factor into the cube roots, so x minus y. Then we square the first term, so x squared. We multiply x and y. We square the second term, so y squared. And this is the part that follows SOAP. So it's minus, plus, plus. I'm just going to erase the SOAP so it's not in our way. Now I'm going to factor the x cubed plus y cubed. Pretty much the same way. The cube roots of those would be x plus y. Then I square the first term, multiply the first and second, and square the second term, and follow the SOAP pattern, so it's plus, minus, plus. And now we are done, because I was saying in my previous video that the longer part of cubics, that part and that part, those parts never factor any farther than that. So you are done. Get rid of that. All right, so that's the answer for that kind. Now, splitting the middle term just looks a little harder with problem number 1 over here. We have to split the middle term because we have the leading coefficient of 4, and there's no GCF that we can take out. So we need something that would multiply to the 4 times the 9, which is 36. So we need something that would multiply to 36 and at the same time add up to negative 12. Well, the two numbers that would work would be negative 6 and negative 6. So we're going to split the middle term. So I recopy the 4x squared. The middle term is going to split into negative 6xy minus another 6xy. So that's just the minus 12 split apart like that. And then I recopy the plus 9y squared. Okay, like that. Then we have 4 terms, so we group. Let's do it this way. Let's change this to plus a negative 6 so that the negative stays with the 6. Now we take a GCF out of both pairs of parentheses. So out of the 4x squared minus 6xy, I could take out a 2x. So that leaves me with 2x minus 3y. Then out of this other parenthesis, negative 6xy plus 9y squared, I can factor out a negative 3y. That leaves me with positive 2x minus 3y. Okay, and then exactly what should have happened did. 2x minus 3y is the same in both. So this 2x minus that 3y goes together in one parenthesis, like right here, 2x minus 3y. And then the blue gets written down, and you might notice that they're exactly the same as each other. And that is correct for this one. That is the answer. You can also write that as 2x minus 3y squared, if your teacher prefers that. Now what you can notice, and this is why I put problem 2 down here, is that this is a type of problem. You don't have to do it in a special way. You can do it like we just did with splitting the middle term. But if you notice at the beginning of a problem that the first term and the last term are perfect squares, you could test out something to the side to see if this special thing would work. The square root of 25x squared is 5x. The square root of 16y squared is 4y. Now if you notice, if I take the 5x times the 4y, 5x times 4y, that's going to be 20xy. And if we double that, it is the 40xy that's in the middle. The reason we would double it is because after you FOIL your factors back together, the middle term would be doubled. So if you notice that these square roots are popping up and you feel comfortable doing this shortcut method, what you can do is take the square root of the first, which is 5x, plus the square root of the last term, which is 4y, and it would be identical in the second parenthesis, and that would be your answer. And you can double check, foiling it back together, you would get a 20xy plus another 20xy, which equals 40xy in the middle. Now this is a shortcut for doing this kind of a perfect square trinomial, so you can do it if it makes sense. If not, just do it like we did number 1 with splitting the middle term. Now on the second page, we have some examples of grouping because there are 4 terms. Now usually you group, I'll erase this, usually you group the first 2 and the second 2 terms together. That is not what we're going to do here because it won't work out. What we are going to do is group 3 and 1 together, or 1 and 3. And you can just kind of guess and check until you find something that works. I know in the first problem that it's going to work really well if I group the first 3 things together and then I have that one by itself. Because now we look at them separately. The first 3 things right here will factor. We need to multiply to 25 and add to negative 10, which would be negative 5 and negative 5. So I know that this would factor into x minus 5 times x minus 5. And then we still have minus y squared. We don't really need parentheses around that, so I'll just leave them off. And then a better way to write x minus 5 times x minus 5 is if I just put that, x minus 5 squared. Alright, now, looking at what we currently have, this is a term, and this is a term. There's 2 terms separated by a minus sign, and we could take their square roots. If we just write to the side a little checking, the square root of x minus 5 squared is x minus 5. And the square root of y squared is y. So these are perfect squares. What we can do in that situation is put the square roots in here. So the square root of the first is x minus 5 minus the square root of the other, which was y. And then again, the square root of the first, x minus 5, plus the square root of the second. And that would be your final answer. All right, now we have another problem we can try this with. This one I can see right away I'm going to group 1 and 3. I'm going to have 81 by itself, and let's make this plus a negative so we don't separate the negative from where it belongs. And if I factor it that way, so first I have this 81. Now what I am going to do is take a negative out of that whole parenthesis. So that makes it become x squared minus 2xy plus y squared. So that's just like taking a GCF out. Now 81, nothing really happens with that. But this part here can factor into x minus y times x minus y, which is the same thing as x minus y squared. And then put the 81 minus back in front. And then just like the first problem, this is now the difference of two perfect squares. If we double check square roots, square root of 81 is 9. Square root of x minus y squared is just x minus y. Keep this x minus y in parentheses as you write everything though, because it's a quantity. So now we are going to factor with the square roots. So the square root of 81, 9, minus the other square root, which was x minus y, in its own pair of parentheses, and then 9 plus the other one, which was x minus y again. And let's just leave it. You can leave it that way, or you can get rid of the inside parentheses by distributing. So 9 minus x minus y, you could do that. And then this was just plus, so it's 9 plus x minus y. And so you could write it like that at the end. And then on our third page, this is kind of a tricky technique, factoring by completing the square. So in our first problem, it looks unfactorable. Like it looks like you wouldn't even be able to factor because there's nothing that multiplies to 16 and adds up to -1. Nothing. But if we make the middle a nice number, then we could factor. Now here's the thing about this. If the middle was, let's say, plus 8x squared, okay, if it was this would be great, it would be good, because multiplies to 16 and adds up to 8, 4 and 4 would work really well. Okay, and you do want to try to keep it the same number. So multiplies to 16, yeah, there's other choices like 2 times 8, 1 times 16, but what works really well is 4 times 4, and that adds up to 8. So our goal is to change this -x squared into a positive 8x squared. So what I'm going to do is take the original equation, x to the 4th. I have a minus x squared there, I can't just get rid of that, but what I could do is add 9x squared to it, because that would make it 8x squared altogether. And I still have a plus 16, I just can't get rid of that. But then what I need to do is balance out my work. I can't just randomly add 9x squared and change the problem, but I could if I subtract 9x squared at the end, because now I have really not changed the problem. So now what I have, if we combine like terms in here, we do have x to the 4th plus 8x squared plus 16, and then minus that 9x squared at the end. And then if we group it 3 and 1, like on that other page, we could proceed and factor everything. So this will factor into x squared plus 4 times x squared plus 4, and the minus 9x squared is at the end. This is the same as having x squared plus 4 squared minus 9x squared. Then we can factor that by doing square roots. So we will have the square root of x squared plus 4 squared. That's a quantity. Let's do this. X squared plus 4, and the square root of 9x squared minus 3x. Okay, I didn't show the work here. Let's do that to the side just in case you're having trouble. X squared plus 4 squared. The square root is just x squared plus 4. That's where I'm getting that. And then the square root of 9x squared is 3x. So that's where I'm getting that. And then in my second factor, I have x squared plus 4 plus 3x. And then you're done. You can just circle that. So let's try that same exact thing with number 2. You notice that the last number is 36. So we would want something that would multiply to 36. And not add up to 11, because that's not going to be the right middle number. But the best thing to multiply to 36 would be 6 and 6. And because of that, then, we would want the middle to be a 12, because then the 6 and 6 would add up to 12. But the middle right now is an 11, so we want to change that, to a 12x squared. Well, we can do that by adding a 1x squared. So I'll have x to the 4th plus 11x squared plus a 1x squared plus the 36 that was there. But I added a 1x squared, so I need to subtract a 1x squared so that I'm not really changing the original problem. Then if we combine like terms right here, we get x to the 4th plus 12x squared plus 36. And then we have that, oops, I shouldn't write that first. We have that minus, I'm just going to say x squared. Okay, and then from here it's like before where you would group. Grouping 3 and 1 would work really well. These 3 factor into x squared plus 6 times x squared plus 6. And then you still have the minus x squared. So these two you could just say are x squared plus 6 squared minus x squared. And then we're going to do factoring this by square roots. And here's the little work to the side. The square root of x squared plus 6 squared is x squared plus 6. This part I'm sure you can do in your head, and then the square root of x squared is x. All right, here I probably will need more room, so I'll write it down here. So the square roots, I will have x squared plus 6 minus the other square root, and then x squared plus 6 plus the other square root. And that is your final answer. You can always check if those last parentheses will factor again, but I was kind of checking as I was talking to you, and I know that they don't factor any farther. So those are just our final answers there.